Okay, let's go to solve briefly the test 3 part 4. Question 1. This is the question 1. It says a baseball is thrown vertically upward and feel no air resistance at its rising. Well, at its rising, the momentum, the mass by the velocity, is becoming smaller and smaller because the force multiplied by delta t is the change in the momentum. The force is the weight going down during the time delta t produces a change in the momentum. So the picture that you need to have in mind always is that this is pi, the initial momentum, and because there is force, mg by delta t going downwards, the new momentum will be this one. After some time delta t, there is force, and the new momentum will be this one. So the momentum is decreasing and decreasing all the time as I'm making the picture here. So the momentum is not conserved. As he's going upwards, it starts with a certain amount of kinetic energy. As he's going upward, the weight do a negative work. So the change in the kinetic energy is negative. So the final kinetic energy is smaller than the initial kinetic energy. So the kinetic energy is smaller, and when he is at the top, the kinetic energy is zero. But going downwards, the weight is positive and the work is positive. So the change in the kinetic energy is positive. So now the kinetic energy increase. So neither the momentum is conserved, neither the kinetic energy is conserved. So let's go to read what it say. It say, both its momentum and kinetic energy are conserved? No, this is no. His kinetic energy is conserved? No. His gravitational potential energy is not conserved. I don't know what it means that gravitational potential energy doesn't change. It should mean it's changing. So this is no. His momentum is not conserved, is true. His mechanical energy is conserved, is true. Potential mass, because there is only forces that are conservative, and forces that are conservative makes the total mechanical energy, kinetic energy plus potential energy, to be conserved. And part E say both his momentum and his mechanical, no, momentum is not conserved. Okay, so D is the correct answer. Let's go to the next one. The next one say like this: a block of mass M, 8.4 kilograms, this one, moving on an horizontal frictionless surface with a speed 4.20 meters per second. So he's moving in this direction with 4.20 meters per second. Makes a perfectly elastic collision with a block of mass M at rest. Okay, perfectly, so the kinetic energy is conserved. After the collision, the 8.4 kilogram blocks recoil with a speed of 0.4. Wow, so this one is moving with 0.4 meters per second to the left. Okay, and the other one, I don't know. In the figure, the block are in contact for a time of 0.20 seconds. The magnitude of the average force on the 8.4 kilogram blocks, while the two blocks are in contact, is closer to, well, okay, let's go to analyze this. The force acting on the time makes a change in the momentum. This is the basic equation. So, What force I have? An unknown force. During how long is acting the force? 0.22 seconds. What is the change in the momentum? mv final minus mv initial. M is 8.4. V final is minus 0.4 because it's going to the left. V initial is 4.2. So V final minus 0.4 minus V initial. If you make the calculation, the force will be 193 newtons. As you know, as you see, the information that they give us is enough to know the force acting on the body. Let's go to another question. Here is another question. It says, 8 gram is 8 by 10 raised to the minus 3 kilograms. Is shot, a bullet is shot to a mass of 4 kilogram blocks at rest on a frictionless horizontal surface. The bullet remains lodged in the block, so it's inside the block. The block moves as an ideal massless spring and compress it 8.7. So the compression of the spring after the collision of the mass with the bullet with the spring is 8.7 centimeters. 8.7 centimeters is 8.7 by 10 to the minus 1 meters. 8.7 centimeters, 10 to the minus 2. 10 to the minus 2, sorry. The spring constant is 2,400 newtons per meter. So it says, what is the initial velocity of the bullet before the collision with the block of 4 kilograms? So initially, I have momentum in the positive x direction. So I have m by v sub I. V sub I is the velocity of the bullet. M is the mass of the bullet. The initial momentum equal to the final momentum. The final momentum is the mass of the bullet with the mass of the block moving at certain v final. That is a known velocity. So the v initial is m plus m divided by m by v sub f. Now, the equation says, when it arrives this to the spring compresses. So it has kinetic energy. There is no potential energy because the height is not changing. The total kinetic energy is converted into elastic kinetic energy at the point of decompression. So this is the total mechanical energy before the collision with the spring, and this is the final mechanical energy after the collision in the point where there is the maximum compression, where there is no kinetic energy. So this equation says that V final is this amount. So I have the V final, so I will put it V final here, square root of this, and I will find V initial because all the data is done. So how I will do it? V initial is m plus m divided by m by v final, m plus m and v final is the square root of this with the x. I'm plugging numbers and find what is the velocity. I didn't do it, sorry. Okay, next problem. When a rigid body rotates about an axis, all the points in the body have the same. When a rigid body rotates about an axis, all the points perform a circular motion around the axis. And all the points, they move together because it's a rigid body, they move together with the same angular velocity. So when one point rotates an angle, like this point rotates the same angle. So they have the same omega, and they have the same change in omega, the same alpha. So this is the two things that they have in common. Same angular velocity, because it's a rigid body, same angular acceleration. So now let's go to read what it says. It says, all the points in the body have the same linear displacement. There is no linear displacement here. There is rotation. Is not the center of mass is not being translated. Have the same angular acceleration. Yes, it's true. They have the same angular acceleration. Same tangential acceleration. No, it's not true. The tangential acceleration is alpha by r. If you are far from the axis, the tangential acceleration is big. If you are next to the axis of rotation, the r is small and the tangential acceleration is small. So it's have not the same. Tangential speed. The tangential speed means to v tangential, v is omega by r. If you are the same thing, if you are far from the axis, you are moving with a tangential velocity. This is the tangential velocity v. This is the tangential velocity. So this point is moving with a tangential velocity smaller than a point that have a bigger radius. So the tangential speed is not the same. And the centripetal acceleration, A centripetal, is v squared divided by r. But v squared divided by r is omega by r squared divided by r, or omega squared by r. The omega is the same, but the centripetal acceleration depends on r. If you are far, it has more centripetal acceleration because the omega is the same one. So have no the same. So the only one is here is the angular acceleration. Okay, this is the only one that is true. Okay, go to the next one. A dumbbell-shaped object is composed by two equal mass m, connected by a rod. So this is the dumbbell, this is two masses, this is the connection of the rod. And the length from here to here, that length that separated two masses are r. He could put d, but he put it r. If I1 is the moment of inertia of the object with respect to the axis passing through the center of the rod and perpendicular to it. So the axis of rotation is this one, this is the axis. So I1 is m1 by the distance square. The distance square r divided by 2 square plus m2, this one, by the distance, this distance square, m by r2 divided by 2 square. So I1 is 1/2, if you make the calculation, 1/2 mr square. And I2 is the moment of inertia with respect to an axis passing through one of the masses. Let's say this is m, and this is the axis of rotation. Now the object will rotate like this through the axis. And now the new moment of inertia, it has another mass distribution, so it means that it has another moment of inertia. The moment of inertia is m1 by r1 squared plus m2 plus r squared, but r squared is 0 here. So the only one that survives is this one. Because this mass is on the axis of rotation, have not radius. So I2 is m by r squared, and I2 is bigger than I1, so the answer is the first one. Let's go to another question. In the figure, point P is at rest, is here. When it is on the x-axis, The time t when p returned to his original position on the x-axis is closest to. When he returned to the original position in the x-axis, the angle that was performed is 2 pi. So this is a motion with constant angular acceleration. So the equation for constant angular acceleration is that theta equal theta 0 plus omega 0 t plus 1/2 a t squared. Sorry, alpha t squared. So theta 0 is 0 initially, omega 0 is 0 because it's a, so theta of t is 1/2 a alpha t squared. When theta is 2 pi, what is t? When theta is 2 pi, t is 2 times 2 pi divided by alpha. But I know alpha. Alpha is 0.01, so t is the square root of this, and I suppose that is 35 seconds, more or less, so this should be the correct answer. Let's go to the next one. The next one, it say like this. It say a wheel has a radius 0.4 meters and have a moment of inertia, of course. A block is suspended from a rope, this block, that is bound to and attached to the figure. The wheel is released from the sun, descend, so the wheel descend 1.5 meters in 2 seconds. Or the average velocity is 1.5 divided by 2, so it's like 0.75 meters per second, the average velocity. But he starts with 0 and he ends with a bigger velocity, probably 1.5 meters per second. 1.5 meters in 2 seconds. In 2 seconds, the average velocity I said is 0.75. So it will finalize with 1.5 meters per second. I think. Well, we'll do it now. Without any slipping on the rope, the tension in the rope during the descent of the block is 20 newtons. So there are 20 newtons applied here, and 20 newtons acting on the wheel. So what is the moment of inertia of the wheel in this case? So this is the data that we have, the radius of the wheel, the displacement in the vertical direction, the time that takes to displace 1.5 meters, and we know that the tension produces angular acceleration here. So there is angular acceleration alpha here. What is the amount of angular acceleration? The torque, T by R. The torque is I by alpha. The torque is the equivalent to the force. The force equal mass by acceleration, but here is a rotational motion, so the sum of all the torque acting on this point, on the center of mass, is T by R. The weight is not having any torque because it's applied to the center of mass. So T by R is I by alpha, so I is T by R divided by alpha. You plug in numbers, T you know, R you know. Alpha is what you have to know. And alpha is being done by the kinematics of the rotational motion. Delta y is a motion with constant acceleration. So delta y have to be 1/2 at squared. So A is 2 times delta y. A is 2 times delta y divided by t squared. So it's 2 times delta y is 1.5 divided by 2 squared is 3/4 of meters seconds squared. This is the acceleration. So it makes an acceleration of 0.75 meters per second every second. So it will end with a final velocity of 1.5 meters per second after 2 seconds. So I was right. So linear acceleration A is alpha by r. I know A, so I know alpha. Alpha is A divided by r. A is the linear acceleration. R is the radius of the wheel. So A is 3/4. And the radius of the wheel is 4 divided by 10, 0.4. So the alpha is 3 divided by 16. So I will plug in 30 divided by 16. I will plug in alpha here, and I will have T by R, T20 R by alpha, 30 divided by 16. And you make the numbers, and you find I, the moment of inertia, and my thing is this amount. Okay, let's go next one. Next one, it's the torque of a system. So there is force acting on this direction. So we are going to find the torque respect to the point O. Respect to an axis that is in this direction. But indeed, if we do it through the point O, will be exactly the same. No way. So the torque is the force by the distance perpendicular to the force, or the force perpendicular to the distance. So here I will do the torque like the force. The force is this one plus this one. This one over the distance this will not produce torque. Is the force perpendicular by the distance. So it's this magnitude cosine of 30, this magnitude is 6. 6 cosine of 30 is this magnitude. By 0.6 is the torque produced by this force. So F1 produces a torque. And the torque of F1 is the magnitude of F1, 6 cosine of 30 by 0.6, by the distance perpendicular. Now, for the force F2, the force F2 is the magnitude of the force perpendicular to the distance. Now, you don't have to make any calculation. It's this by this. The force and the distance perpendicular to the force. So the force is F2, which is 9. And the distance is 0.8. Now there is a question of sign. This force produce a counterclockwise, a clockwise rotation. So it's negative. So tau 1 is negative. Now this force produces a counterclockwise rotation, so it's a positive torque. The sum is, well, this by this. And my thing is like 4.2, something like this, 4.1. Is positive torque or negative torque? It's a positive torque. You have more force, F2 is 9 newtons. You see they have more force, so it will produce more torque in this direction. So the torque is counterclockwise, meaning that the total torque is positive, 4.1. Let's go to the next one. The next one will say like this. Will say, let's go to read it. It's in the figure, there is a mass of 31.77 kilogram. It's attached to a string around a cylinder, the cylinder of radius 10 centimeters. So if it's a cylinder, the moment of inertia is 1/2 mr squared. Okay, it's suspended from the ceiling, then released. It advanced at delta y was 5.7 meters from above the floor. How long does it take to reach the floor? He's asking about time. How long is the time to arrive to the floor? Means how long is the time to perform the distance 5.7 meters? In how long he will perform the distance 5.7 meters. So there is a motion of constant acceleration, and we need to find the acceleration. So the torque is acting on the wheel, on the cylinder, and produce a rotation, an angular acceleration in this direction. So T by R is I by alpha. So T by R is I by alpha, but alpha is the acceleration of the center of mass of this body, of the 31.77 kilograms, is the acceleration divided by the radius of the cylinder. So this is the first Newton equation for rotation applied to the cylinder. The second equation is the standard Newton equation for translation applied to the mass m of 31.70.7. So I have mg going downwards, I have acceleration positive going downwards, mg is positive, so the sum of all the forces is mg positive minus t equal ma positive. So mg minus t is from here. T is I divided by r squared multiplied by a. A center of mass and a center of mass. A of the mass little m, this one. Okay. So this equation have only one unknown, the a. So I want to solve for a. If I solve for a, I will find the acceleration. The acceleration will be mg divided by m plus I divided by r squared. If you solve for a, you will pass this to the side. Factor common is a that multiply by m will produce this term, and a that multiply by this will produce this term. So this is the a. I'm plugging numbers, I have the a. But I know now that y is y0 minus a t squared divided by 2. So if I place this equation from the floor, initially the object was at 5.7 meters, so y0 is 5.7 meters. And finally, the object will arrive here when y equals 0. So the equation y of t will be y0 minus at squared divided by 2. Perfect. When y is equal 0, I will find the time when y equals 0. If y equals 0, minus 1.5, minus 5.7 will be minus 8 squared divided by 2. So t squared will be 2 times 5.7 divided by a. But I know a. Find the square root, and you will find the time. Now let's go. And what is the correct answer for this question? Let me try to see what you can do the numbers, but let me remember if I did it. Maybe, wow. You have to be careful here because there are two things that are very, very similar. So if you use G like 10, maybe you will not know which one is the correct answer. I think it's around here. So you do it, you can do it. Okay, let's go to this problem. This problem is a little bit more sophisticated than others, but they are not quite difficult. So it says like this. Let me read it to remember. In the figure, 2 blocks of mass 2 kilograms and 3 kilograms. 2 kilograms is smaller than 3 kilograms, but it doesn't matter because he is at the horizontal table, and what is important is the tension here that pull the mass of 3 kilograms. So even a body of 1 gram here will produce a tension here, and the object will accelerate. Of course, 1 gram will make this mass of 3 kilograms to accelerate smaller. But here the problem is similar as the Newton problem that we have solved, but now the cylinder can rotate. And this is the differences. Now the acceleration that you obtain going downwards is a smaller acceleration than in the case when the cylinder is not rotating, like in the chapter 4 and 5. So it's a 3 kilogram is connected with a light string. A pulley, the moment of inertia, here they give you the mass, they give you the moment of inertia, they give you the radius of the cylinder, and they give you the coefficient of friction. Here there is friction. So there is a force of friction going in this direction through the 3 kilogram mass. Okay, how we will do this problem, and what it's asking is, using energy method, find the speed of the upper block just as it has moved 0.6 meters. So delta y is 0.6 meters. Okay, the things is to apply this equation that is the idea. The work, the net work, is the change in the kinetic energy. The net work is what work? Is the work that the weight is doing. But the weight is only doing work on this little mass m, because on this mass the weight is going downwards, and when he moves 3g, when he moves, it's not doing any work because the force is perpendicular to the displacement. So the work is the work by the weight that will be the work acting on this body, on the 2 kilogram body. The work of the friction, this is the total work, the work of the friction, and the work of the friction is negative and is acting only on this body. There is no friction here. Okay. And there is more work. There is the work of the weight here, the work on the friction here. Should I consider the work of the tension that the tension is doing? No. Why not? Because this tension will produce a positive work when he moves from here to here, to the right, while this tension will produce a negative work. The net work refers to the external forces. So, the work of the weight plus the work of the non-conservative forces, the friction, is the change in the kinetic energy. Now, the work of the weight is minus the change in the potential energy. So the equation that I have recreated is that the work of the non-conservative force is the change in the kinetic energy minus delta U plus delta U. The work of the non-conservative forces, the friction, is the change in the mechanical energy. Change in K plus change in U. Now we apply our equation, and you have to do the work because I don't have any calculators. So the force of the non-conservative force of the friction is minus F friction by delta S. When he moves delta S is when the body when the other body displays 0.6 meter going downwards, he moved also 0.6. So the work of the friction is minus mu mg by delta S. So I have the data here. All the data, this is nothing unknown. Now, the mechanical energy final is the mechanical energy of the body M1 the mechanical energy, kinetic energy of the body M2, plus the rotational kinetic energy of the cylinder, plus the potential energy of the mass M2. So this is kinetic energy plus potential energy. If I choose the floor, the level of the mass M equal 3 as my base, if I choose this floor like this, this is the floor, and I imagine that the object is here, this one is here, no? So it has no potential energy, but it doesn't matter. This just is to make something simplified. You can imagine that the object is here if you want at certain height, because what it counts is how much advanced, the 0.6 meter. The 0.6 meter. So the mechanical energy, the final mechanical energy is kinetic energy of the first, kinetic energy of the one that is holding, is going downwards, kinetic energy of the cylinder, and potential energy of the body too. If I choose the reference at the floor, this H will be negative. So this potential energy will be negative. So this is the total mechanical energy final. And the initial mechanical energy is 0, because the first object is not moving, the second object is not moving, the cylinder have not kinetic energy, and I consider that the mass M2 have not H. So minus 0. Minus 0. So now if I work number, I can find VF. So you do it and you find VF. Okay, I think that I found 1.28, but I used G equal 9.8, and I think that you should use 10 meters per second square. That's why I'm going to cite for the exam to use G equal 9.8. So if you use G equal 9.8, you will, that is smaller, you will, well, it's a smaller acceleration. If it's a smaller acceleration going downwards, you should find well, I don't know, you should find a velocity maybe a little bit big than this one. Well, you do it with the numbers. This. But here is the calculation, everything is known. The only unknown is the VF. So you do it and good luck. I hope you enjoy the problem. So the idea of this problem is the work of the non-conservative forces made a change in the mechanical energy. Mechanical energy final minus mechanical energy initial, the change is the work of the non-conservative forces. The second idea is that considering the mechanical energy, you have to consider the term of rotation, kinetic energy of rotation of the cylinder. This term didn't appear in the chapter 7 about work because we didn't consider rotation. So that's all. Good luck.